Welcome back, Algebra II students. Today we have Chapter 1.9, Notation for Recursive Formulas. So we did the recursive formulas for the sequences in our last class. And it turns out I was already using the notation because I knew you guys were ready for it. So this chapter really is just more practice with the recursive formulas. So here we have a sequence, just a list of numbers that follows a pattern, 17, 12, 7, 2, -3. Find the recursive formula. Remember, for the recursive formula, we need two things. We need the first term, so T1 equals, just copy it down, 17. And then we need to tell how to get to the next term from the previous term. So we look at the sequence and say, okay, the pattern is you just subtract 5 from 17 to get 12, and then subtract 5 to get to 7, and subtract 5 to get to the 2. So what we have to do is Tn equals, the symbol for previous term is Tn minus 1, and the pattern is to subtract 5. So it's Tn equals Tn minus 1 minus 5 for integers n bigger than or equal to 2, because we already took care of the first term, n equal 1. And just a reminder about the notation, how we represent the terms. Tn represents the nth term. So if n is 4, it would be the T4 would be the fourth term. And Tn minus 1 is going to be the n minus 1th term. So if it's minus 1 term from the n, that means it's the previous term. That's how we write the previous term. Which is useful when we're trying to write the sequences where we can tell the pattern based on how to get to the next step from the previous step. So that's why the recursive formula is useful. Okay, let's look at another example. So this time, consider the sequence. I'm gonna give you the recursive formula for it. So if it's the recursive formula, you know it's gonna have two things. First, I have to give you the first step. So T1 equals 60, first term, and Tn equals, I have to tell you how to get to the next term from the previous term. So it's going to be 2 times Tn minus 1. And again, that is for n's that are bigger than or equal to 2, because we already took care of n equal 1 in the first step. Okay, question is find the first 4 terms of this sequence. So the first term is easy. We just read it off of T1. So T1 is 60. The first term is always given in the recursive formula. To get T2, it's 2 times T1, or T1 was 60, so it's 2 times 60, so it's 120. The third term, 2 times the previous term, which is T2, and that's 120, so it's 240. And then we have to get the first 4 terms, so T4 is 2 times T3, which is 2 times 240, so that means it's 480. And we can stop there because we just need the first 4 terms. So I'll just write it as a list, as a sequence, 60, 120, 240, 480, and then just the ... to represent that it's going to go on from here, but we just need the first 4 terms. Okay, done. We'll highlight our answer. Okay, let's look at another example. In this example, I want to show how sometimes it's easier to use the explicit formula than the recursive, so let's explore that. Okay, so first I'm going to define this sequence using the recursive. So first step, T1 equals 1, and then how do you get the current term from the previous term? Tn equals Tn minus 1 plus n for integers where n is bigger than or equal to 2, because n equal 1 is already taken care of in the first step. Alright, so we want to find the first 4 terms. Alright, that's not too bad. The first term is pretty easy. You just copy it off. T1 equals 1. T2 equals T1 plus 2, which is 1 plus 2 equals 3. The third term is the T2, which is 3, plus n, which is 3, so we get 6. And then T4 equals T3, which is 6, plus n, which is 4, so we get 10. All right, not too bad. We got the first 4 terms, 1, 3, 6, 10. We write it as a list to represent the sequence. and then highlight our answer. So everything's going well so far. But I get to this question where I need to find the 100th term. Now, if you think about it, that is going to be a huge pain, because to get to the 100th term, I'm going to have to find the 99, 98, 97, 96, 95, 94, all the way back through. I have to find all the terms leading up to it. And that's why I'm crying. I'm putting my sad face, because that means I have to find 99 other terms. So the recursive formula, it's useful for writing the pattern, because a lot of times it can be easier to come up with a pattern based on the previous term. But the weakness that it has is if you need to find a term that's way down the line of your list, in this case the 100th term, it's really not good for that, because for the recursive, since it depends on the previous term, if you want to find the 100th term, you have to find all the terms up to 1 through 99. So in this case, we actually want to use the explicit formula. And we actually did this sequence before when we were doing the explicit formulas. It's that sequence 1, 3, 6, 10. It's that triangle sequence that we get from, just to remind you how we got the explicit formula, where the explicit formula is really good for finding the 100th term, because we only have to put in n is 100 and we'll get the value of the term. So remember, the way this worked is it's basically a triangle where it's half the area of a rectangle, where the width is n and the height is n plus 1. So to get to term n, it's n times n is the width, n plus 1 is the height, and then divide by 2 because it's just half of it. It's the triangle. So that's the explicit formula. You might remember it from, we did it in class last week. And this is really good for finding the 100th term, because we can just put in n is 100, so it's 100 times 101 divided by 2, so it's 50 times 101, so it's 5,050, and we got the right answer. So hopefully this example, what I want you to take away is, when is the recursive formula useful and when is the explicit formula useful, so you know when you should use which one. And the summary is that if you need to find a term that's, maybe above the 10th, or maybe even sooner than that, but anytime you need to find a term that's, way down the line of your list, you want to use the explicit. Okay. So the last sequence to consider is going to be this one, 1, 1, 2, 3, 5, 8. So we want to find the recursive formula for this sequence. This is a pretty famous sequence, and I'll explain why once we find the formula for it. So if you've seen this before, I think this is one of those sequences you have to see at least once before you kind of look for it. The pattern is that if you look at this 2, you get that by adding the previous 2 terms. The 1 plus the 1 gives me the 2. And the 3 I get by adding the previous 2 terms, 1 plus 2. And to get the 5, I add the 2 previous terms, 2 plus 3. And to get the 8, I add the 2 previous terms, 3 plus 5. And that is going to be our pattern. To get the next term would be 13, because it's going to be 8 plus 5. Okay, so we're going to write the recursive formula. In this case, since it depends, the pattern starts on the 3rd term, I'm going to give the first 2 terms, t1 equals 1 and t2 equals 1. And then for tn, it's equal to the previous term plus the previous term. So how do we write that? Tn minus 1 is the previous term, plus Tn minus 2 is the previous term, like 2 steps back from where I am. And that's the recursive formula, and this one's called the Fibonacci sequence, after this Italian mathematician, and he created some code based on this sequence, and it's used in like Da Vinci Code and a lot of like famous mystery books. But yeah, okay, that's it. We'll see you for the next class. Thank you.